hope everyone had some positive things from their Labor Day weekend. Lots of sweating and being outside. Part of that, I imagine. Crazy hot. Before we get too far into class, from discussion with a few different students, I realized that one of the problems in looking at some of the data on Pearson, one of the homework problems that was pretty challenging.
Number 7.
Was number 7?
Felt that.
With the converting the units and trying to decide whether a test result meant that someone was stable or unstable. Sound familiar?
It was the one after that.
Okay, so one thing I wanted to point out that might make a significant difference, and maybe I should do it up on the digital platform so that people at home can see, is, so this is unrelated to the question that's there, but it was something to the extent of some sort of units that were like this, and you had to compare them to a value that was in totally different units. The most important thing for me in looking at this, whenever you see unit/unit, is to think about that as two completely separate units and to write it out as a conversion factor. So you have a conversion factor that for every deciliter, this person has this many millimoles. Don't worry if you don't know what millimoles is for now. We're not going to talk about moles for a while in this class, but you need to know that it's a unit. So I want you to rewrite that in a way that makes more sense. That for every 1.42 times 10 to the negative second millimoles, that is found in 1 deciliter. Or 1 deciliter contains this many millimoles. And then maybe you're trying to get it in liters and micromoles or something. So you have to say, well, how do I convert from this set of units to the set of units that are actually reported in the table of what's stable and not? So you're going to go ahead and each one of these, you're going to say, I want to convert from deciliters to liters. So we know that there's 10 deciliters in every 1 liter. And then we want to convert, let's say, from millimoles, and the question maybe gives us micromoles. I don't know. Then we can convert from millimoles to moles. And then if we needed to convert from moles to another unit, we could do that. But the big take-home of all of those questions, all those components of that one question, were that if you see this written out as something / something unit, then you don't even start to see how it all fits together in dimensional analysis. So hopefully that, if you were uncomfortable with that process, this will kind of help you set it up and start to do those calculations. I do want you trying to practice looking for scientific notation and trying to decide to estimate what your size should be in the end instead of plugging everything into the calculator, because you are going to get quicker and quicker at doing this throughout the course of the semester. And in your lines of work, it is likely that if you see scientific notation or metric system units that are milli, deca, micro, whatever, you're going to need to have that quick kind of mental math. So the quicker you can kind of approximate that answer, the better off you're going to be. We're going to spend some more time doing unit conversions today, and it's going to be rough for the first few minutes, but we're going to practice more and more use of unit conversion. So our first exam is supposed to be next Wednesday. I prefer to have the first exam as soon as I can in the semester. What that does is it allows for a check-in. If you feel like you're getting it and you're kind of sitting back and you're not necessarily spending a lot of extra time reading or practicing, and then you get to the first exam and you do really well, then you're like, okay, I am getting it, like it is as easy as it feels. A lot of times that's not the case. A lot of times students will get to exam 1 in any class that you take, but chemistry is probably more so than a lot of others, and you'll say, ooh, I can't actually do these problems in a timed setting with a little bit of pressure. So what that tells you is, okay, now's the time I can reset. It's just the first exam of 4, so it's not going to be that big of a deal. Okay? I like to have that as early in the semester as I can, so that it's not really far into the semester, and then you're like, oh crap, like we're already this far in, I'm going to have to change my study habits, and it's really late. So the earlier the better. With that said, I was talking to Ms. Katoum about trying to figure out how to line up workshop, the part of the beginning of lab, to be a study tool before the exam. But as you know, Monday didn't have lab this week, and so we're trying to figure out how to do that schedule so that if we do give the exam, that everyone gets a same chance to get the support of the review that we would do in workshop. So by tomorrow evening, I'll decide what day the exam is on. It will be in class. They're always going to be in class, so it doesn't change the fact that you would need to come to class, and you already do that. So I will try to notify you by the end of the day tomorrow what the exact date of the exam is.
Are the exams all multiple choice?
I will do half multiple choice most likely and half short answer. And our fearless team member, Anil, will help me grade those short answer components. So we would like to try to get partial credit where we can, and we'd like to see your work. So a lot of the stuff we're doing, we're going to say specifically, explicitly show your steps of unit conversion, and you have to show that setup. Okay? So earlier in the semester when I said you have to do that, I want to see it. Yes?
When I was reading the syllabus, it said something about an index card.
Yep. As we get closer to the exam, we'll talk a bit more about that. But for tonight, I'll just mention that 3x5, whatever the normal index card is, you can handwrite on that anything you want. You can write example problems or whatever. However, I think I will put a restriction that you cannot put the metric system on there. So that means that you cannot write what I just had up there, right? 1,000 milli in a full, or 10 deci in a regular. Especially, once again, in medical field, you're going to need to know what those letters mean. That deci means a tenth, that milli means 1,000th. So I do want you to learn those sooner rather than later. Maybe make flashcards, something like that. Aside from that, there will be no other restrictions. You can put anything you want on those note cards. It has to be handwritten, has to be your own, and it has to be 3.5 by 5. And I'll collect them at the end. It's a way to force you to make a study tool to say what's the most important things we've done and to put it all on a piece of paper. And it gives you a little bit of a crutch on the exam. All right. So with all that said, I want to do a lot today. It means I'm going to need dedication from everyone in here to be as on point that if you get stuck, raise your hand as quickly as you can to have one of the team members. I think we have the whole team in here today. So make sure to flag someone down if you get stuck to start moving along. The worst thing you can do for your own learning today is to kind of sit there and be like, I'll just wait until everyone else answers it and then I'll figure it out. It's not a good way to do it. Okay? So we're going to finish a majority of packet 1 today. And we're going to finish packet 2. You see where this is going? Packet 1 is the nuclear atom. It has a chem activity 1 on it, and it has this image. Do you mind coming and grabbing it? If anyone forgot their packet 1, I have 3 copies. Does anyone need a copy of chem activity 1 who does not have theirs? If you don't already, please get a 3-ring binder and keep all your chem stuff in it. Sorry, I set yours right on that corner there. Trying to make it easy. A 3-ring, I try to hole punch everything and staple it together. This is your set of study tools that you have for the exam. All right, so this is question, where are we at? Question 9? This is question 12. Maybe? Basically question 12. All right. It maybe is a deviation of question 12, but it relates to the image on the front. And go ahead, if you have not already, we have almost everyone's clicked on their response. I want you to answer this question, and I want you to describe how you found that answer, and what's a way that you can easily find answers to a question like this. So take 1 minute, finish entering your answer, and then discuss with the person beside you how you would answer this question. What's the logic you use to get there, the process. Before class started? Great.
When we're counting this, and you see that there are 10,
Should be. What do you mean should be?
Where it should be, or I think where it is early on. Right.
All right. I would love to hear one of those discussions that your group had about the logic. How do we answer this question? Maybe first, what is your answer? And then how do you answer a question like this? Go ahead, Summer.
So when it's a negative charge, you're supposed to add that to the electron.
Okay, so you're saying that there's a negative up here.
Right. Which means that it will be 2 more electrons to whatever your answer is.
2 more electrons to, what do you mean?
To whatever the atomic number. I mean the proton.
Why? Okay, so mathematically there's a formula like this, right? But I want to get beyond the math. I want you to have the math, but also to know where it comes from. Donald, do you want to add to that? Sorry, I can't hear you. How do we know that?
Because it's oxygen and plus, so if it's 16, you can, and there's no, it doesn't say there's extra neutrons, you can assume that the neutrons.
No!
No?
One of the few times I'll aggressively call out no in class. Because it's a really valid point to bring up. Most of the time with some of the elements we see, you've been like, oh, it's half of the mass number. But we don't ever want to make that assumption, okay? So, when we look at this symbol, if we wrote it in the form that your homework wanted you to write all of the symbols, right? There was the Z, there was the X, there was the A. So what is missing in this depiction? The one in the bottom left corner, right? I think they call that A, right? What would that be for this particular element?
8.
It's 8. And how do we know that it's 8? What's the first thing you said, Donald? Not the second one I disagreed with.
Oh, because we know that's 8 because it's the atomic mass unit.
Great. And Anil, can you point out where that is on the periodic table? So there is redundancy built into this system. It means that this O means that we don't need to say 8 protons, because if we have 8 protons, it's automatically O, it's oxygen. This means this, this means this. They mean the same thing, so it's redundant. You don't need both. But sometimes we write a lot in there, and it helps you think about what that top number means. So what does that top number, that 16, mean?
That's the weight. But like the mass.
Something to do with mass. It's called the mass number. So what is the mass number, which is this guy up here? Can someone explain that? Hand raised. Yes.
The number of protons plus the number of neutrons.
Why are the number of protons plus the number of neutrons? Why is that? Why are those referred to as the mass number?
Because they are what make up the majority of the mass of the element, because electrons don't really have.
Amazing. Couldn't have said it better myself. Electrons have such a small amount of mass that you're saying, if I took one oxygen atom, if I could take the magic school bus and go way down to the point, remember we did that little simulation last week where you dove way down and you saw the core of the atom? And we looked at that. This particular one would have 8 protons, so we know it's oxygen. And then it also has 8 other particles that have mass, those neutrons. And then it might have some electrons, depending on more or less electrons. That's not going to change how heavy that atom is. It's not going to change this number. But it is going to change this number. So if we cycle all the way back now, and we go back to that 2 minus, we had a description. I think Summer was describing that, right? So if we know it's oxygen, we know that there's 8 protons. So how do we end up with a 2 minus? Do you want to take another, or say that over again, or does someone else want to, do you want to pass it to someone else? Okay, would anyone else like to jump on? Go ahead, Monica.
Would that mean that there were 10 neutrons?
10 what?
Wait a minute. Yeah, like,
Okay, so that -2 in the top right corner means in this particular case, we know that we have 8 protons because we know it's oxygen. We know that we have 8 neutrons. So that means that there's 8 positively charged particles. And if we have a whole bunch of positive and a whole bunch of negative, but overall all the pluses and the negatives equal a minus 2. If we had the same number, if we had 8 and 8, we would have a 0 overall charge. Because we have 10 electrons, and we have 8 protons, that means that overall we have 2 more of the negatively charged particles than we do the positively charged ones. Okay, so it's all about the relative number of them. What if we said, well, couldn't this also just be, couldn't we have 8 electrons and 6 protons? Wouldn't that give us the same, isn't that exactly what that is too? What do you think?
No, because there's 6 protons, so it's a different element.
Fantastic. So what would this element or ion actually be? Carbon. Specifically carbon with what charge? So this is carbon 2 minus. And we don't know anything about neutrons, I didn't tell you that, so. Okay, so yes, it is about the difference in electrons and protons, but we need to keep in mind that the number of protons dictates what element it is. All right, what about our second question here? And I think this is the first time we're asking one of these types of questions. So if you think it's 1 and 2, enter 12 and then send. If you think it's just 1, hit 1, send. If you think it's 1 and 3, hit 13, send. Does that make sense how I want the responses? It's kind of like a multi-select. Okay, we have 43 responses. Let's do another 5 or 10 seconds. All right, closing out. Let's see if I can toggle. All right, so a majority of the class is saying 1 and 3. Why is that? Which? So if we talk about the mass number, right, that's only talking about how many protons and neutrons and why. Why don't we include electrons? They weigh such a small amount. They weigh about 10,000 times less than either the proton or the neutron. How much exactly does a neutron weigh? 1. All right, we're going to come back to that, what AMU is and what that means. All right, so our goals for today's class that we're going to be flying through is by the end of this class, from various different representations, I want you to be able to determine the identity of an element or isotope from any representation. I don't know, that's kind of poorly written. I want you to be able to calculate exactly how many of the subatomic particles exist within an element, kind of like we just did. And then we're going to spend some time applying unit conversions to these units that we just talked about, AMU, and how that relates to grams. And then we're going to spend the last half of class talking about logic and how we can use that to talk about what if we have one isotope and another one, how do we describe how much of each we have? We're also going to, as well as using logic to think about those, we're going to do some calculations as well. And one thing about this part of class is I don't want to lose touch with that video that I showed last time. Linus Pauling talking about an order. The reason that you take chemistry is to understand the fundamental particles that make up matter. I don't want you to get so lost in the theory of memorizing an atom is this, and this is protons, this is neutrons, this is electrons. So all of the things that we're discussing in this class have been discovered by scientists that have studied these things at extreme detail and have come up with theories. And so I just wanted to spend a very brief minute showing you a bit of a clip by Neil deGrasse Tyson, talking about what science is, because I feel like sometimes we lose track of what that means.
One of the great things about science is that it is an entire exercise in finding what is true. Your hypothesis, you test it. I get a result. A rival of mine double checks it because they think I might be wrong. They perform an even better experiment than I did, and they find out, hey, this experiment matches. Oh my gosh, we're onto something here. And out of this rises a new emergent truth. It does it better than anything else we have ever come up with as human beings. This is science. It's not something to toy with. It's not something to say, I choose not to believe E equals MC squared. You don't have that option. When you have an established scientific emergent truth, it is true whether or not you believe in it. And the sooner you understand that, the faster we can get on with the political conversations about how to solve the problems that face us.
So I'll post that video. There's parts on either end. I didn't want it to come across as a political statement because he does have a little bit of a frustration, let's say, with those who make political decisions that stand in denial of science. So I'll post that in my slides. You can go and watch the rest of the video if you have not seen it. He's a very powerful speaker and an amazing physicist. So when I say that all the things that we're talking about are based off of work that people have done, it really is that people have studied. They thought this is how it works. They go study it. They find a result that either matches or denies what they looked at. Then they go again and they say, okay, well, maybe that wasn't quite right. Let's look at this instead. And then the data either supports or refutes that. And then someone rival comes in and says, well, let me review that, see if I can replicate it. If they can't replicate it, we're back to the drawing board. So this process of science, I think a lot of people, especially in the media, it gets portrayed as one expert says something and we're just supposed to believe them. And so the theory, the term theory in science means that it has been experimented on, it has been validated by multiple people, it has been, the data, the conglomerate of data, a huge amount of data supports this conclusion, and so that's called a theory. So the atomic theory that we're going to be talking about, that we're using for all these descriptions, is exactly that. That it helps us predict what happens in the world to an insanely precise level, and so that is the theory that we use until we're proven otherwise. And we're open to looking at data that might prove that otherwise. So, some of the early pioneers in this field was a Russian physicist, Mendeleev. He is one of the people who is given most of the credit for setting up the periodic table that we use today. And unlike people before him, he decided that he saw a trend in all these different elements that exist based on the number of protons that there are. Previously they said, well, how heavy are they? But sometimes you can have an atom that is much heavier because it has a larger number of neutrons than protons. And so it can get kind of confusing. And so this periodic table that you can see up here around antimony over xenon, you can see that the mass, atomic mass at the bottom of these doesn't go in order if we arrange it just by the number of protons. And so what he discovered, and many others have confirmed since, is that the properties of an element are much more dictated by the number of protons that they have and the arrangement of the electrons within them than it is by how heavy they are. Neutrons don't play nearly as much of a role in the properties of atoms as it is for the number of protons that are there. That's true up until radioactive elements, and then the number of neutrons really does make it unstable. So our periodic table as we know it looks like this. Does anyone, maybe from earlier classes, do you recall what the name of the columns are? Not the specific names. What do you call a column and what do we call a row? Does anyone remember what those are? So there's two names. There's period and there's group. Which one is which? Which one is a row and which one is a column? Morgan?
Column, a group?
Correct. And what we're going to find in the next week, most likely before exam 1, is that the properties of elements are most similar to the ones above them and below them. And that's why we call it a group, is because that group has similar properties. So then the ones that go across, we call that a period. So the rows are called periods. And you'll see a lot of these numbers at the very top of the groups. And those are technically called the group numbers. The ones I want you to focus on are the ones with the A's. Those 8 groups are called the main groups. Because those are ones that most of, especially biological chemistry, focuses on. The ones in the middle, all of these ones down here that don't have A's, that have B's, these are called transition metals. They all have properties that are fairly similar. They're metallic in nature, which means they conduct electricity, and they have certain visual properties to them. And in this class, we're going to focus very little on this big block of elements, these groups, 3B through 2B. They're kind of strangely organized.
What did you say A's were called again?
The main group elements. Yep, so the main group. So if I say main group 3, what column is that? That's 13. 3A. All right? And honestly, most of our time is going to be spent studying this top right-hand corner and then the left 2 groups. Each symbol does give us a lot of information, and by the end of today's class, I want you to be able to talk about what that bottom number is and means, that 52.00, but we're not going to get into that just yet. So let's go into activity 1, and I want you to complete that first table, which is exercise 1. With your knowledge, fill in the entire table. You can start question 2 if you finish that, but let's go ahead and take about 3 minutes to fill in that table. Make sure you can write the symbols, what is the atomic number, the mass number, and the number of electrons. Try not to go too far ahead because I'm going to be really specific in questions 2 and beyond how we're going to do those problems. If you get stuck at all, please call one of us over. So this is POGIL activity 1, exercise 1, this table here. Phosphorus 31 is the first element in the table.
Oh, sorry.
Once you're done, or if you're stuck, ask the person next to you, make sure to confirm your work.
Probably just straight up for this part.
Isn't the mass number the same as the isotope number? So it really is just straightforward.
He's agreeing with me.
He looks nervous.
Because if it's like in a volume, and this is also assuming that, because,
It's the same electron. Because that's basically I had to write it out.
So the last one I done at 26, number of electrons for that.
I not got that far.
Nickel.
this is what's called paternalism. So basically, it's the theory that
If it's negative, we add it, even if it's left out,
It makes
I mean,
sense.
because that's what you
It's
did,
a proton
if it was negative at first, we added it.
Yeah, that makes sense. Then you have more of the positive protons or something.
You can, when you know that protons equal electrons. However, we have
they happen all at the same time. So basically, if you pick up this piece of paper and putting it back down, it has happened and already will happen.
but I wouldn't do like
So basically, think of instead of the universe one at a time, it's a line and these branches are this is what we're referred to as the universe. Instead, think of the universe
But here's the way to that.
backwards, it's everything is just there.
But what you said was a really good way to think about it.
Assuming that we were able to look at everything
Positive and extreme, so like a negative charge.
this
So if you end up with like a higher amount of electrons, it's going to be negative. If you end up with a higher amount of protons,
it could be even smaller than not even it's just like assuming that we were not in where we are right now. Then everything that will ever happen.
yes, it's positive, that means that there's more
Assuming that there is, that this isn't the case.
I think that makes sense because
It doesn't have
Other universes that have multiple clouds at the same time.
so that's why
We could have but we can't because we don't have enough to prove
What?
any of this or any of this. Yeah.
because the mass number is 16.
Are you on this one? Yep. Good.
It's okay.
That must be.
Oh, it's the from the city. I literally got this because
Ooh, you're right, you gotta do it.
I think it's much like finish your thoughts and then we're gonna go through that problem.
it has a positive charge, so there would be less electrons to make it.
because nickel will always have nickel will always have 28.
Since you have more neutrons, you know, less electrons.
It's just because technically that's
Good for catching on, I didn't notice that.
the reason why it's changed.
We're usually we're sure you're talking about us.
All right, let's go ahead and talk through. I'm going to ask for a volunteer to complete one row at a time. Is that okay? So I need 4 volunteers. Can I have my first volunteer for P31? Tell me your name again. I can't. Shelby. Great. Can you go ahead and talk through the first one? Yeah. So with 31P, atomic number 15, what is the mass number and number of electrons?
Mass number is 31 and number of electrons is 15.
Okay. Any questions about that? How did you find 15 electrons?
Since it doesn't have a negative oxygen particle, like 2 minus number of protons and electrons.
Great. So we know it's neutral from the symbol, the way it's drawn, so we know that it has the same number of protons and electrons. Okay, can I have a volunteer for 018? Ankar?
Yeah, I got 8 for the atomic number and then 18 for the mass number.
Okay, how'd you get 8 for the atomic number?
I just looked at the periodic table and to see the atomic number and then for the mass
Atomic number for?
Oxygen.
Great. So once again, we have the letter that tells us what the atomic number is, or if we have the atomic number, it tells us the letter. And then the mass number was the one written up above.
Right.
So one of the things that, going back to what I harped on Donald for, not to throw you under the bus again, this is an example of where you don't have an equal number of protons and neutrons. There are a lot of these cases. So the most common form of oxygen that we find in the environment, if we go out and if we were able to pull the air from out in front of us, most of the air that we see is going to be oxygen 16. But every once in a while, we'll find an oxygen atom that has 2 more neutrons, that's oxygen 18. We actually call that heavy oxygen, because it has 2 more mass particles in it. What about the third line? What is the missing symbol for the third line? Can I have a new voice? Jay?
I think it's A39 and then a +1 charge.
What do y'all think? How'd you come up with that?
So the mass number is 39, so that's where I got the 39 from. And then there's one more of the atomic number than the number of electrons. And so it's the opposite. It would be minus 1. Wait, I confused myself.
So this is where I like to just say the relative number. So there's one more of the positive things than the negative things, right? There's one more proton than there's electrons. So that's going to give us a +1 overall charge. So I agree with what you have. I just really think it's important to talk through how we got there. So, and how do we know it's potassium? Okay? Because we know the atomic number, right? And so you can just look that up. Great. And the last row. Chris.
28 and 26.
28 for the atomic number. How'd you find that?
Because nickel has 28. Its atomic number is 28.
Great. And then the number of electrons?
Is 26 because there's 2 less electrons than protons.
Great. 2 less of the negatively charged particles than the positive because we know it's a +2 overall charge. 2 more of the positive ones. Okay, fantastic. Go ahead and start working on question number 2. I want you to try to set this up using dimensional analysis or unit conversion approach. I think you can probably do this mathematically. You have enough information. I'm going to give you literally 1 minute, and then we'll work on it together, okay? I don't want you to get too lost. That's why I'm only doing 1 minute. I'm not expecting you to solve it in the 1 minute. Make sure you try to write something down. It's very important to try to write something down for an approach of how you would answer question number 1A. Yes. I know we use heavy water, which has H2, which is what you have in the front page. H2 has one extra neutron atom, so that can be used for looking at the distribution of water that we put into someone or into a system. Does it go here or there? We know that we most likely source of that. I just don't need
Are we supposed to be
There's some synthetic reasons we can talk about after class, but yeah.
converting from AMU to grams?
All right, let's go ahead and do a clicker question. Start us off. Please go ahead and answer our clicker question. It's going to get us into answering question 2. Couple more seconds.
Onyx is stuck loading.
All right, closing out.
Wait, I'm like stuck loading. So,
Close it, open it again.
Yeah, mine logged me out. I had to like go back in.
All right, how about a volunteer? What does AMU stand for? New voice, yes. Great. Atomic mass unit. So from that, I agree with the majority of you that AMU is a measurement of mass. What are some other measurements of mass that we're more familiar with? Grams. Milligrams. Kilograms. Pounds. Ounces. Stones. Anyone from Britain? I don't think we have any British people. They have a lot of useless measures. They don't use most of them anymore, right? So one of the hardest parts about this component of the class is that when people are introduced to a new unit of mass, it's really hard to wrap your head around. Is the unit of AMU, is one AMU a lot of mass, or a very little amount of mass, or a very, very, very large amount of mass? It's really little. Literally, the name has atomic mass unit in it, right? So if we're looking at a single atom, we can pick out and say, well, there's a proton, that weighs about 1 AMU. It's like saying this little pen cap, this weighs about 1 gram, right? This is something that I can hold physically in my hand at this scale. If we have an AMU, do you think I could hold that in my hand and feel any difference if I had that in my hand? How small is an AMU compared to a gram? Do we have anywhere to tell us exactly how close together they are? Or how far different? Where's that, John Paul?
I'm just saying that you picked up the homework packet.
I did pick up the homework packet. Donald, did you notice it anywhere on here?
I found it.
Where'd you find it?
At the very front page.
Very first page, we have a conversion factor. Did you miss that when I said read the first page very carefully? No? Everyone caught that, I'm sure. Okay. So 1 AMU is equivalent to 1.6606 times 10 to the negative 24th grams. Can we picture how small that is? Like, I can't even picture how small that is. It is so ridiculously small. So if we were to write out, instead of 1 gram, like I said this pen cap was, we're saying that it's not a hundredth of this, a tenth, a millionth, a billion. It's like a billion of AMUs you would need to say how heavy this thing is. So it's like an insanely small mass unit. So what this question is asking you to do, question 2, is how do we express the mass of one hydrogen atom in grams? Do we know how heavy it is in AMU? Is it 1.008? Is it 1.00794?
Not this one.
We have to use all those.
Not that number. That number, all of these numbers, some people started using these already. We're not to that point. You can't use these yet. And you'll see why, hopefully before the end of class. Remember, go to the front of the page. Front page. How heavy is a 1H atom? No, 1H atom has a little image here. I don't want Donald answering all the questions. Come on, help out. Dustin?
1.0078
Fantastic. The units are really important, right? It doesn't just weigh 1.0078 grams, because that would be really heavy for one hydrogen atom, right? It doesn't weigh this much. So it weighs 1.0078 grams. So how would we write this as dimensional analysis? How would we show the mass of one 1H atom in grams? What's our starting unit, our starting quantity? So I'm going to go to this question. All right. So our first starting point is a single 1H atom over 1. Is that where everyone started? Okay. So now go ahead and fill out the rest. I want you to go from the number of atoms to, what are we going to have as our answer units? Grams. Go ahead and take one more minute, try to set up this conversion factors, the set of conversions. See how many you need in order to get grams of 1H over here. Do you expect it to be a big number or a small number? Focus on setting it up. Don't worry so much about calculating it yet.
That's equal to 1.H atom. But that is not 1.H atom. So this is a conversion factor we can figure out how to use it. That's a conversion factor. That's a conversion factor. It's your starting point. How can you use those conversion factors after this? Yeah.
All right, you ready to walk through the first one together? I saw a lot of people saying, okay, I know that you said we start like this, but I'm not going to start like that. All right, it's going to be really important that we set it up this way, and I'll show you why in a second. What conversion factors do we have to move away from the number of them that might be able to get us into, let's say, how much they weigh? What conversion factor do we know that we can use here? Chris?
One hydrogen atom is equal to 1.0078 AMU.
Amazing. We just said it, right? We just talked about this as a class. We said that we know every 1H atom weighs 1.0078 AMU. Now we have a conversion factor that lets us go, well, if I know how many, I can tell you how heavy they are in AMU. If I have a mass of 1H atoms, I could use this the other way and tell you how many of them there are. Either way, we can use that conversion factor. So now if we stopped, we know how heavy the 1H atom is, because we only have one of them. So maybe we even put like a 1 of them up here. Does that get us the answer we need? So how do we get from the mass of AMU to the mass in grams, Tony?
You do it 1.6606 times 10 to the negative 24 grams on the top.
No, I'm not joking. All right, so go ahead now and use that approach for the next two problems. So this is problem exercises 3 and 4. Make sure you set it up as dimensional analysis. Think about what your starting quantity is now, what conversion factor is appropriate to use, and what unit you're trying to get to.
You're tricking me right now, and I feel like I'm correct.
That's what I'm wondering. It's kind of what I'm thinking. Who did you do first, right?
I give it times 12 to convert it.
Hang on.
Well, kind of, because we don't have
Okay. Is this uncomfortable? Do you see why I focus so much on unit conversion? Because when we start doing units that you aren't comfortable with, it becomes much more difficult to do all these steps. So, do I have someone who's willing to volunteer to write their work up here? Anyone to write on the screen? Jay? You're so shy. I was hoping. Okay.
Now my handwriting bad, so I'm gonna try.
I zoomed in so you can write pretty big. You can just write in here.
Okay.
You
If
put your
you're-
hand down because it's Apple Pencil and I won't recognize your hand.
Oh, my bad. Yeah, thanks. Right.
So as she's writing her answer up there, go ahead and make sure you finish writing out your answer, your approach, and then try the next problem as well if you haven't done that yet. Yeah, sure. If you're ready to do
X
5.
right there
If you haven't
instead
done
of
4,
a
do 3 and 4. And then
Okay.
Okay.
Try to keep moving.
And remember, use units.
Did I use units?
So you know
What's the
units of that one.
atoms?
Yep.
It's a long line. Okay.
12 about 16.
Over one. I can just put one. Atoms? Look, well,
You're talking about a specific atom. What would that atom be?
carbon.
Mm-hmm.
So I put, that's
Which
it.
carbon? Any carbon? Carbon 13, okay?
No, 12. Did that look right? That look weird.
Okay.
No,
I'm not helping. Okay.
We gonna say that's right. Y'all don't judge me too harshly.
I know it's really
Oh, thanks.
sorry.
Okay.
I just don't think I'm setting it up right. All right. Are we talking about 4 or 3?
Well, both, because they're kind of the same. But I set it up like.
Okay. So you start out with atoms, right? Mm-hmm. And you know you can't go from atoms to grams. You can't do that.
Yeah.
So what would you have to put on the bottom right here to be able to go forward?
I can't go. It's in.
So you would have in what is 12 AMU? What specifically are you talking about?
The number of. Wait, which is really 9. So
Okay,
can I
so
just
you
put
put it
9
up here too.
Don't round.
Don't round?
Nope.
Oh,
Okay.
I don't know. Wait, okay. How do you erase?
Round to
You start out with
360.
4.35 times
Oh,
26
okay, okay.
atoms of
You're good.
carbon, right? And then in
Okay, so
one
can I
atom of carbon,
So should this be
not
8.670?
1 gram.
Because it's 8.668?
Okay.
No, it should
And once you know that, and then you
six,
go from
seven,
AMU,
yeah.
and then
Okay.
go in
For now, just write the
AMU,
units.
there's that many
Oh,
grams.
okay. I don't know how to erase.
So just
So
make sure
7,
you don't use 1
0.
gram down here.
And then this is.
Because you know 1 gram
Wait,
would not equal that because you have this conversion.
atoms,
factor.
8. So is it atoms?
So that calculation, I know it's not equal to 1 gram.
I don't know.
It's really
Go ahead and take your final thing.
it's
Gotta grab it, you gotta
X
get moving.
amount of
Come on.
grams.
Yeah.
Like
I
I'm
don't
trying to
know.
figure out
Put a
how
unit,
many
put a
grams
unit.
it is,
I don't
but
know.
When you do dimensional analysis,
Oops, sorry. I'm very Okay. What do we think? So, does everyone agree? Let's go step by step. Does everyone agree with the first part of this? Huh? What's that? What's grams? Okay. I'll put that in there for you. So let's go through step by step. Far left side. Does everyone agree with what's written here as a starting quantity? We just have this many atoms. That's it.
I put that as my final thing, but it's like 0.
Okay, doesn't matter if it's carbon 12 atoms. Doesn't matter if it's carbon 13 atoms. Does that change anything? Absolutely. This next conversion factor is specific only for that isotope. So we would have had to write in, I'm going to do purple here. This is carbon 12 atoms. Because if we know it's carbon 12 atoms, that defines this conversion factor. Now we know that for every 1 carbon 12 atom, they weigh 12 AMU. It's a multiplication sign, sorry. Not very clear. So we converted from the number of carbon 12 atoms, so how many of them, to how heavy they are in AMU. And then we said, well, we know how heavy they are in AMU. Does everyone agree with this next conversion factor?
Well, they need the grams.
Okay, so once again, maybe it's being put on the spot, but we have to have the units we're converting from and to. So that's every 1 AMU is this fraction of a gram. And if we do that, we calculate out our answer, then we get a value. Does everyone agree with that value? Does that seem reasonable? Why does it not seem reasonable? Before you do any calculations, we should always make sure to think about what type of answer are we expecting. Is it big? Is it small? Supposed to be small. We have 10 to the 6th times 10-ish, which means 10 to the 7 and then 10 to the negative 24. If we add those exponents, it's going to be 10 to the negative 15th, 17th, something in that range, right? So I know that we might have just missed our scientific notation here. So what scientific notation should we have beside that number? What should it be times 10 to the negative 17th, and we can put the grams over here, right? And then scientific notation and sig figs. Do we agree with the sig figs for this? How many sig figs should we have? We should only limit our sig figs by the number that was probably measured. This is an exact number as far as we're concerned. So we should have 3 sig figs, so we probably just want to get rid of that 0 there, and then I'm going to rewrite her 7. Okay? How do we feel about this problem? So one of the difficult parts of this is that this conversion factor only depends on what it is that we're converting from. You cannot just put in 1.0078 AMU is any element you want. This has to be a logical statement that this is equal to this, the top and the bottom of that fraction. Yes, Morgan?
I know the units are important, but on the test, are you going to mark us off as being a unit?
So if you...
Aside from the final answer, like in the work.
If you forget to put a unit in here, I'm not going to be happy. I will deduct points, yes. It'll be partial credit. So everything's going to be partial credit if you show your work. I do want to see really specific units, not just atoms, not just carbon atoms, but carbon 12, if that's what you're talking about. I want to make sure that you're at 12 AMU, or 13 point, what is the carbon 13 one? If we did this with carbon 13, it would be 13.0034 AMU for every 1 carbon 13 atom. All right? Questions? Yes?
Where did you get the 17?
The times 10 to the negative 17th? So that is, one, you can just plug everything in your calculator, and that's the answer you get. But also, I estimated that by saying, well, this is 10 to the 6th. Here's another power of 10. So that's 10 to the 7th. 10 to the negative 24th. So that comes out to about 10 to the negative 17th.
Wait, where was the other power of 10?
12. 12 is the power of, it's 10 or bigger. So this could be 1.2 times 10 to the 1st is another way to write that. All right. Did anyone do the next question? Question number 4. So how do we set that up? I'm going to write this on the big clear screen. So you said 6.0. What? Are we sure we can use that conversion factor? Yeah. It's carbon 12, so we're using carbon 12's conversion factor. Great.
And then I multiply that by the 1.6606 times 10 to the negative 23 grams. I'm sorry, 24 grams over 1 AMU.
What did you find?
Oh, I got 12.00 grams.
Is that suspicious? What stands out to us about that answer? What's that? So you're talking about scientific notation. There's really big scientific notation, really small scientific notation. So they kind of cancel each other out. True. Donald? True. Scientific notation, that's how you could write this answer as well. I'm going to leave it in this form specifically for a reason. What's unique about that number compared to the equations we just had above? What's that?
No, you can go ahead.
No, go for it.
Alright, well, the number that they gave us, it's basically an inverse of the atomic mass unit.
So if you do 1 over that number on the far left, it is the number on the top right. So mathematically, they cancel each other out. That's why we have 12 equals 12. You see that? So we have a new conversion factor. 6.022 times 10 to the 23rd carbon-12 atoms is 12 grams. Does that look like another conversion factor we just used? So this is one of the special numbers in carbon. This number is called Avogadro's number. When you have exactly this many of something, then this relationship is true for one carbon-12 atom. This relationship, the same numeric value, is true in grams. What's another name for Avogadro's number of things? That's called a mole. A mole is this many things. So if you have this many carbon-12 atoms, it weighs 12 grams. If you have one carbon-12 atom, it also weighs 12, but what is the weight of a carbon-12 atom? It's those really, really, really small units. See a connection between those? Don't ever tell me that this many carbon-12 atoms weighs 12 AMU, or that one carbon-12 atom weighs this many grams. Those are not true. But the relationship, the proportionality between 1 mole and 12 grams is the same as 1 carbon-12 atom and 12 AMU. Ready to start on packet 12? Or packet 2? Hold up, I still have 30 seconds. Still have 30 seconds. The rest of packet 1 is going to be really good practice for you to go through for the exam, which is upcoming, and I will tell you the exact date of that. Activity number 2, we will start and finish in the first 20 minutes of class on Monday. What does that mean about homework? The homework has stuff from activity 2 on it. I'm going to go home tonight, and when I send an announcement about the exam date, I'm also going to send you an update on the due date of this, homework assignment. If I extend it to, let's say, we do Tuesday night instead of Sunday night, does that mean you wait until Tuesday to do the homework? Okay, so whatever the extension is, please go in and try to do a little bit of the work on the homework, as much as you're comfortable with. And then we'll do the part that matches activity 2 after class on Tuesday. After class on Monday, sorry. Fair? So try to do as much as you can before Sunday, and then Monday will help for the rest of activity, or your extra homework. All right, have a good night. Your extra marks. Thank you, John Paul.